welcome back to this afternoon session. It's my pleasure to introduce Rob Morris, my colleague. So he finished his PhD in 2006 in Memphis and spent some time at Cambridge, then in Tel Aviv, and came to IMPA in 2010. Right? He won many prizes, so almost all math societies. So I remember the European prize in combinatorics, the prize of the Brazilian Math Society, the one from the Caribbean and Latin American Union, the Fulkerson Prize of the AMS, then the prize of the Mathematical Council of Americas. So many, I'm certainly forgetting some other prizes. So it's a great pleasure to introduce Robert.
Oh, thank you. Thank you, Claudia, for the very kind welcome. It's a great honor to be speaking at this conference at home. So as a slight apology to start with, the thing I'm talking about today is a little different from most of the things I work on these days. But it's a very sort of long-running project that is very interwound with my own history with IMPA. So that was one very good reason I wanted to talk about it today. Other reasons it was another wonderful thing that came out of this very long-running project was how I met Ugo for the first time and got to work with him. So one of my first sort of the big results was proved while I was a postdoc here that I'll mention later. And also, I've just spent the entire pandemic basically writing down an extremely long proof that I won't be telling you anything about the proof, but I'll tell you what we proved with Paul Smith, mostly with Paul Smith. So this is all, the final result that I want to talk about is joint work with Paul Ballister, who's now in Oxford, Bela Bolabash, who's in Cambridge, and Paul Smith, who was a postdoc at IMPA a couple of times, now works in finance in London. And I'll mention some other joint works, some older work with Yoshi Balog, with Ugo, and with Ivailo Hatarski, is a very clever young guy working with Cristina Tornelli in Paris, and also Fabio Martinelli. So I'm going to mention lots of things. Okay, so I want to start by motivating the problem, and I'm lucky that Ugo already gave a wonderful motivation for this morning. So one of our motivations is the Ising model. So Ugo talked about the static Ising model of magnetism, but I want to think about the dynamic model. So instead of just saying, okay, here's the distribution, what does it look like? Say, okay, you start with some, I don't know, maybe you're away from equilibrium, and then you update. Do you remember the red dot that was moving around? So you do that, and then you kind of move towards equilibrium, and how does that happen? How long does it take? So each site has a random clock, it rings, and the site kind of updates depending on its neighborhood. And so a very basic question is, suppose you start away from equilibrium, suppose you start with everyone being minus, for example, how long does it take you to relax? This was solved in 2 dimensions by Dengerpour and Sherman, and higher dimensions by Cerf and Manzo. And some of these names you will see again a bit later in the talk. So it turns out that the thing I'm going to talk about, which is a simpler version of the Ising model, is actually sort of a key combinatorial tool in the proofs of some of these results. So if you want to understand how the Ising model is changing over time, it turns out that actually sort of perhaps the heart of the problem is a simpler combinatorial question that I'll describe. Yeah, so one question you might have is, so they solve the nearest neighbor interaction, you just look at the guys who are right next to you. What if you depend on people who are further away or in some more complicated way? Right? So Ugo also touched on this a little earlier. Okay, so here's another thing you might be interested in. You might be interested in glass. So what is glass? Glass is you take something and you kind of cool it very quickly and it solidifies. But if you look microscopically, it looks like a liquid. So that's why you can see through it. And it turns out it's not really understood how this happens or why it happens. So it's an important open problem in condensed matter physics. And there are some models called constrained models that we introduced some time ago to model this. And what happens? So you start off with, so you're in a similar sort of situation to the Ising model. You're resampling with random clocks. But the rule now is you're only allowed to resample if your neighborhood looks a certain way. Okay? So instead of thinking of the general models, it's perhaps nice to think of just a one-dimensional, so a very beautiful one-dimensional model called the East model. So you're just on the line Z, and then if you want to update, what you do is you look at the guy left, on your left, you say, if he is infected, let's say, then you're allowed to update. It sounds incredibly simple, but actually this model is quite intricate. There was some lovely combinatorial work done by Percy with Chung and Graham about 20 years ago. And there's been a great deal of progress on this in recent years by Evailo, Fabio and Christina, and also Lo Maresh, another student of Christina Tondinelli. And once again, a really sort of key combinatorial lemma, or sort of several of the key combinatorial techniques in their sort of analytic techniques come from what I'm going to talk about. Okay, so these are motivations, and it's somewhat surprising these very complex, non-monotone models of statistical physics. Really, what it comes down to is something that's a bit simpler and more combinatorial. Okay, so what am I actually going to talk about? I'm going to talk about monotone cellular automata. So what are these? These are monotone models of these things. So instead of allowing things to go from plus to minus and minus to plus, you only allow things to go in one direction. Okay? Which simplifies things enormously. Right? It seems like it would simplify way too much and it'd be totally useless. And it's surprising, actually, it still turns out to be useful. And I'll try and explain a little bit why that happens. So e.g. these two models. And coming from the opposite perspective, there are also very general versions of what's known as bootstrap percolation, which I'll describe in the next slide. So for those who know, that's what it is, but I'll tell you in a few seconds. Okay, so what are we going to do today? So I want to motivate things in physical physics. Well, great, that's done. I want to tell you the definition of the model we're going to talk about. I'm going to spend some time talking about this simpler example, which is called our neighbor bootstrap percolation. It's been very well studied. And then I'm going to, at the end of the talk, tell you a bit about general models, first in 2 dimensions, and then the most recent work is in higher dimensions. Okay, that's the plan. Okay, oh, and please ask questions. I'm trying to make, I tried to design it so it's slow enough so everyone understands everything. So if you don't understand something, please let me know. It's my fault. Okay, so what's the process? So this definition is a tiny bit tricky, so let's just think about it. So we're going to take a finite collection of finite subsets of ZD. So now instead of working in just Z, we're working in, I'm going to draw Z squared, the limit of my drawing capability. And we're just going to take a collection of finite subsets. So let's suppose we put the origin, I'm going to use the squares as being the entry. So this is the origin. So maybe this will be a possible x, just those 4 points. You take a finite collection of these things. And you take a set of initially infected vertices, which I'm going to call A. Okay? And then this infection spreads through the population. So if you're thinking about the Ising model, you should think that, okay, almost everything is minus, but there's just a few pluses dotted around. And then those pluses have some chance to spread and infect their neighbors. Okay, so what happens? At time 0, A is infected. Everything that's infected stays infected. So at time t plus 1, what are the new things that are infected? You're infected if one of these sets X, translated by U, is already infected. So these four sites can infect this one, okay, in the example. Okay, so there are various local configurations that can infect you if they're already infected. Okay, okay, and we write this closure as the set of eventually infected sites, and that's what we're interested in, saying, okay, given a set A, what happens if you run this forever? What are the things that could be infected? So the example that we're going to talk about for maybe about 10 or 20 minutes is when U consists of all subsets of your nearest neighbors of size R. So what does that mean? That means you get infected if you have at least R infected neighbors. Okay? If you have at least R infected neighbors, one of these R sets is infected, and therefore you get infected. Okay? And as I mentioned, in the applications above, mentioned previously, this was sort of understanding the corresponding U bootstrap process, this monotone process, was sort of a key step in understanding what was going on. Okay, so to really make sure we understand, here's a picture of what happens in the very simplest case, the two-neighbor model in Z squared. So you get infected. These are the initially infected sites. Who gets infected? People with two neighbors out of the four up, down, left, and right. So who gets infected in the first step? These two. They each have two infected neighbors. Once they've been infected, this guy now has two infected neighbors. So he gets infected, and then the infection spreads. And look, it forms a little rectangle. Okay? And now, if you look at this guy below, he'll infect, with that rectangle, all of these things to form a new rectangle. And then with this guy, you get a bigger rectangle, and a bigger rectangle, and a bigger one, and then you infect everybody. Okay? So you can see that from a very sparse set, these sites that are close together, they're clustering, forming these rectangles, this droplet, which is then growing and infecting everyone. Okay? Okay. Okay, so what can we say about this R neighbor model? That was the two-neighbor model. R just means you need R neighbors. Well, so again, thinking about the Ising model, say, if you start off with this, you're almost all minus, but randomly you have some pluses. So we might think we're infecting things at the start randomly, independently of random probability P, and then seeing what those pluses can go on and cause. Okay, so here's a definition. The critical probability, the smallest p, such if you do this on the d-dimensional lattice, infinite lattice now, then you infect everybody. So what density do you need at the start to infect everybody? And it's perhaps a little surprising to note, or not to note, but it was proved by Schoenman, this perhaps surprising result, that when R is at most d, this critical probability is 0. So this 1, when R is greater than d, your probability is 1, is easy to see, because if you have a little cube that's completely uninfected, each vertex only has d neighbors outside, so it can never be invaded from the outside. Okay, so it's not so difficult to see that PC is 1 if R is bigger than d. So the content of this theorem is this 0 here. If R is smaller than d, then any positive density at the beginning will cause everyone to be infected. Okay. So let me prove this in 2 dimensions, which was first done by Van Enter a little earlier. So we're going to start off, we're going to infect things independently at random probability p, where p is very small. So what do we find? Well, p is positive, we have an infinite amount of space, so somewhere we'll find a huge square of infected sites. Now, because it's so big, bigger than 1 over p, say, you're likely to find an infected vertex on each side. But what happens when you have a big square with an infected vertex on the side? This guy next to it has 1 neighbor inside, 1 neighbor above, so he gets infected. The infection spreads down and spreads up and fills the whole side. Right? So this will cause this square to grow by 2, by 1 in each direction. So the probability it fails to grow is probably this doesn't happen, which is like 1 minus p to the n. But p is positive, so that's summable. So you're done. That's the proof. Okay. The very astute or very awake will have noticed I cheated very slightly because I used the same randomness to find the square and to grow it. But you get around that just by sprinkling in 2 rounds. So just throw down 1 set and then throw down another. But yeah, don't worry about it. Okay, that's the proof. That's the whole proof. It's very simple, right? So So how did Sherman prove it in higher dimensions? Well, okay, let me draw a picture in 3 dimensions at least, to give you some idea. So let's find a nice 3-dimensional cube of infected sites. Now, suppose you're doing D equals R equals 3. So you need 3 neighbors to be infected. Everyone in this face has 1 neighbor inside. This is all infected. So you need 2 more neighbors inside this square. So this looks like a D equals R equals 2 process. So you can use induction and say, okay, I know if I have positive P, I'm likely to grow here. I'm likely to find some infected square here. It's likely to grow. That's not enough. You need a clever renormalization trick to make the induction work. But that's basically the key idea. Okay? So how does a droplet in D dimensions grow? It grows via some, on the side of the droplet, you find a smaller droplet. On the side of that droplet, you find a smaller droplet. On the side of that droplet, you find a smaller droplet, and so on. You have sort of these levels of droplets. Okay, so just to restate it, so Sherman proved that, so I've restated it here with a slight difference. Instead of working on the infinite lattice, I'm working now on a n by n by n by n torus. And the result is now the same. It just means that you converge to 0, converge to 1, as n tends to infinity. And notice that for the induction, you needed this, right? Because here we're working on some finite chunk of the lattice. We're not working on the infinite lattice when we're on a face. Right? This also allows you to ask more detailed questions like, how fast does it go to 0? Right? So how small is this probability, this PC really? Okay. Right. Please. Right, thank you, yes. So in the infinite lattice, this was a 1, because by the 0-1 law, it's either 0 or 1. Sorry, so it could have been a half. But yeah, so here we just pick an arbitrary number between 0 and 1. So yeah, the half doesn't really matter. But yeah, thank you. Thank you for pointing that out. Yep. And sorry, I guess I'm also saying I'm putting a U here when I'm doing the U bootstrap process, and I'm putting an R here if I'm doing the R neighbor process. Okay, that's for convenience. Okay, thank you. Please do ask if
Can this process not grow by rectangles but some sparse structures?
So, yes, very nice question. In the 2 neighbor process on Z squared, it just grows by rectangles, or on ZD by cuboids. But as soon as R is 3 or more, then that's not true anymore. You get more complicated structures. But the way the proofs work is to show that the dominant way of growing, in some sense, is via droplets. But the droplets are no longer necessarily, in more complicated models, they're no longer rectangles, they're more complicated polygons, or in higher dimensions, polytopes. And a lot of the issues are dealing with, the geometry of, high-dimensional polytopes. Yeah, thank you. More questions? Okay, so the first result in this direction was found by Ising and Lebowitz, who showed that in the 2 neighbor model, then you get something like this. So why should that be the case? Well, if you're working in n by n, so how large I'm going to get rid of this picture. Start again. Yeah, so for D equals R equals 2, say, then how big a square do you have to find that's infected? You have to find one that's size basically 1 over p. Once it's size 1 over p, it's got a good chance of growing. How unlikely is that? Well, it's roughly e to the minus 1 over p. Because, so this is the hardest scale to grow at, and each step costs you a constant factor. And so when this is roughly the volume of your world, like 1 over n squared, that's when you can find it. Okay, so you need your n to be e to the 1 over p in order to be able to find one of these droplets that can then grow. So this explains very roughly why the answer should be 1 over log n in 2 dimensions. What about in 3 dimensions? So now d equals 3, r equals 2. Now you need a single site on this whole side. So you only need 1 over root p length sides to have area 1 over p. So this becomes a 1 over root p, and that corresponds to a 1 over log n squared. Okay? And the same thing in higher dimensions. So this is not a proof, but it's a sort of an explanation of where these numbers come from. Okay? You're analyzing how likely is this droplet to grow. Okay? For r is at least 3, the life is much more difficult. And it took more than 10 years to make this step, and exactly for the reason mentioned, your droplets are no longer these nice, simple objects always. But it turns out that you can control it. And so why do you get this 1 over log n behavior? Well, you need to find a droplet of size. So this sort of suggests that your droplet has size about log n. But to grow on the side, you have to find a droplet inside here, which is size log of the side length, a sort of log n size. And that log n has to be big enough that when you can find vertices on the side and grow. So that should be about 1 over p. Okay? So in 3 dimensions, you have a droplet. It's about size log n, because that's the size you can find. To grow on the sides of it, you need to find a droplet, a 2-dimensional droplet of size log n, and log n has to be big enough to be able to grow. Okay? Once again, nothing like a proof, but this is where the behavior is coming from. Okay. How am I doing? Okay. And this is generalized by Cerf and Manzo. So you remember I mentioned earlier, so Sherman's name already appeared, and Cerf and Manzo also. So their work on this bootstrap model informed their later work on the Ising model. So this really was a sort of an important step. They generalized this to general R and D. Okay. So right. So the next natural question is what's the right constant in this theta? The theta is up to constant factors. So it's determined by Holroyd in 2 dimensions. A sort of somewhat surprising pi squared over 18 appears. And then, so this is when I guess I first appear on the scene, and this is also how I met Ugo. So when I was a postdoc at IMPA in 2007, I managed to figure out with Yoji and Bela how to determine the constant for arbitrary DNR. And after posting, so we posted the 3-dimensional version of the archive. And then I got an email from a young, I think, master's student at the time, or maybe even undergrad. Where's Ugo? Yeah. You're a master's student already? Already a master's student. Okay, it's not quite so bad. Who had independently proved this, and with actually a much nicer way of doing the really key step in the proof. Ugo had a much nicer way. So we wrote a joint paper doing the general case. So yeah, I don't feel so bad now that I've known Ugo longer for being upstaged by a master's student. Oh yeah, I'm sorry. So lambda is some explicit constant. Okay. So this is the time I thought, okay, that's the end of the story. We solved the big problem. I'm going to go and do other things. Like, there's nothing else to do here. Okay, it's all over. And so I was very surprised when, I guess, don't know, a year or two after this, I heard from Bela that with his then two students, Paul Smith and Andrew Russell, that they'd written a paper on this incredibly general family of models, which, if you'd asked me the day before they told me if you could say anything about it, I would have said, there's no way you can say anything. right? It's hopeless. Like, what are you even doing? Like, stop wasting your time. But so they come up with a this very beautiful definition that I told you, and they managed to come up with this very simple and elegant partition of all of these families into just 3 classes. And what do they prove? So let me tell you so roughly what these 3 families are. So supercritical models are, roughly speaking, models for which you can find some kind of bounded size droplet that all by itself, without any help from outside, will just grow in some direction. Okay? It'll just grow and affect everyone in its path. Okay? So these families have polynomial thresholds, because, right, you just need to find this thing somewhere, and it's bounded size. It's sort of size big O1. Okay, that's supercritical. The next class were things they called critical families. Those are things that have polylogarithmic thresholds like the 2-neighbor model. So in critical models, then this doesn't happen, but you can find a much larger droplet which can grow with the help of sort of little bits of dust. So if you find sort of suitable dust on the way, then it can grow. Okay? But it can't do it by itself. Like our droplets needed an infected site in each column to go to the right. Okay, so these are critical things. And then the remaining families they didn't know how to deal with, but they called them subcritical and conjectured that for those, the situation was very different, that you didn't get this droplet-like behavior. These things just don't grow. So when P is small, then you just get these little bounded components. So they behave much more like traditional percolation that the models that Ugo mentioned. Okay? They have really a sort of a non-trivial phase transition. This was proved a year or 2 later by Paul and Baylor with Michał Pokutski. I'm sorry, if there are Polish people here, I very much apologize. So both Pauls and Baylor. This is a nice renormalization argument. Right, and so what was this classification? So it depended on what they called a set of stable directions. So what are the set of stable directions? Well, they're a subset of the circle, S1. And so when is a direction U stable? Well, let's take the half space in direction U and ask whether there exists one of our families X inside it. If there is a family X inside it, so that would then infect the origin, then you're unstable. Otherwise, you're stable. Okay, so you're unstable if you would grow in that direction with the help of the entire half space. Otherwise, you're stable, you just get stuck there. Okay? Okay. And so what did they prove? So for any 2-dimensional update family, one of the following 3 things holds. So what do you need the stable set what property of the stable set will allow a bounded size droplet to grow in some direction? What you need is an entire semicircle that is unstable. If you have an entire semicircle that's unstable, then you can grow in the direction of the center of that semicircle. Okay? And then your bounded size droplet will grow. If that doesn't happen, that means in every semicircle there's at least one stable direction, then you're critical as long as there's some semicircle that only has a finite number of stable directions. Okay? And finally, if every semicircle has an infinite number of stable directions, which is always an interval in 2 dimensions, then your PC is bounded away from 0, that you behave like more classical percolation models. Okay? There's only these 3 possible behaviors in 2 dimensions. Okay? There are sort of 3 universality classes, if you like, of behaviors. Okay. Okay, so a natural next question is, okay, can we determine these constants, right? This one and this one. Can we say something more precise? And it turns out, somewhat surprisingly, that for this one, which seems like the easiest one, you can't. This constant is incomputable, not computable. What do you say? Like if you take a Turing, for each Turing machine, you can define a supercritical 2-dimensional family U, such that determining this alpha, the exponent, would solve the halting problem for that Turing machine. Right? So these things are really quite complex. Right? They're not as simple as they perhaps seem at first. So really, this one we have no hope for. Right? You can't do it. Okay, what about this one? And that one, it turns out you can. So with Bela and Ugo and Paul, we proved that if you're critical 2-dimensional family, so there's 2 things can happen. So rather than define these things, I'll do some examples in a second that tell you what they are. So right, either you're balanced, and then your exponent is 1 over alpha. Alpha is always a positive integer. Or you're unbalanced, in which it's the same, except there's this extra funny polylog-log term. Okay? So this determines the up to a constant factor. This is the threshold for every critical 2-dimensional model. Okay. So what are these things? Okay, let me do some examples. So right, so this is the 2-neighbor model, okay, that we already saw earlier. So your neighborhood, you get infected if you have at least 2 of your 4 nearest neighbors are infected. So first, what's the stable set? The stable set is just 4 points, because if you can't go to the right without help, you can't go up, you can't go down, you can't go left, but any diagonal half space will just grow and infect everybody, right? If you take any diagonal half space, then the guy on the side will have 1 neighbor, will have 2 neighbors inside. So this thing will just grow. Okay, so the stable set is very simple. Now I'm going to put some numbers on those stable directions, which are essentially the number of extra sites you need in order to grow. So it's not quite that. It's a bit more complicated, but at least for this model, you need 1 extra site in order to fill in an extra row, right? And then this tells you that you're balanced and your alpha is 1. So why is that? Well, your alpha is 1 because if you look at the easiest semicircle and you look at the hardest direction, that's 1. So there exists a semicircle in which every direction has difficulty at most 1. And you're balanced because when I said that, I didn't say if my semicircle was open or closed, and it didn't matter. If it doesn't matter if the semicircle is open or closed, you're balanced. If it makes a difference, you're unbalanced. Okay? Here's another model, anisotropic model. So this is you need 3 of these 6 neighbors. Your stable set is the same. But now, to grow right or left, you only need help of 1 guy, because you already have 2 inside. But to go up or down, you need 2 more sites. So those have difficulty 2. So now, what is our alpha? Our alpha is 1, because there's an open semicircle with difficulty 1, the one on the right or the one on the left. But we're unbalanced because there isn't a closed semicircle with the same property. Any closed semicircle contains a direction of difficulty 2. And what happens with this model is instead of growing in a nice symmetric way in all directions, it's much easier to grow this in left or right than it is up or down. So your droplet ends up looking like a very long, sort of this one-dimensional object before it's finally long enough that it can grow vertically. That makes it sound like it should be easier to deal with. Actually, these are harder to deal with, somewhat surprisingly. And then here's a third model, also we'll say called the Duarte model. So now it's not symmetric anymore. So you can only be infected from the left, or up or down. You need two of these neighbors. So now your stable set is everything on the left is stable. You just can't grow left at all. On the right, you have a stable direction directly to the right. So everything to the left, we say, is infinitely difficult, because you just can't grow that way. It doesn't matter how much help you have. You can't grow. And to the right, you need an extra 1 help. So now our alpha is again 1, because you have an open semicircle with difficulty 1, and you're unbalanced because you don't have a closed semicircle with the same property. Okay? Yeah. So Duarte is sort of an archetypical, like, difficult model to deal with. Okay, so I have 3 minutes left, I think. It just about gives me time to tell you the main result. Okay, so sorry. So this is what we proved. So this 2014 plus plus is a bit of a joke. The paper has finally, as of a couple of weeks ago, been accepted. So it was with the same journal for 8 years. But yeah, it has now. It is actually going to appear. Okay, so here's the conjecture we made. So we conjectured that in d dimensions there should be these d plus 1 universality classes. So you should either be supercritical if there's a bounded size droplet that grows. You should be subcritical if you look like typical percolation. And otherwise, you should be critical, and you should look a bit like one of the R neighbor models. There should be some R for which you look like you behave in the very global behavior should look like the corresponding R neighbor model. Right, there's a natural definition in terms of the stable set, which is now, the stable set is now in SD minus 1, not in S1, right? You have a direction in every direction of RD, and you should be supercritical if there's an empty hemisphere, and subcritical if there are non-zero measure in each hemisphere. And that's what we eventually, after many years of work, finally proved. Yeah. So we also determined the value of R for every model, and for the same reason I mentioned before, if R is strictly less than D, then the constant of power is uncomputable. If R equals D, then it should be computable, but seems difficult. It seems very difficult to do. And I should perhaps say that one of the great difficulties in proving this theorem is dealing with the higher dimensional geometry, so these d-dimensional polytopes with many faces, and also the geometry of the high-dimensional sphere. So a lot of the difficulties are in proving properties of the stable set that we need in the proof. Right, so I'll just finish by saying thank you. So that's Paul Smith in roughly 2014, I would guess. Yeah. So thanks for your attention, and happy birthday to IMPA.
So questions?
Should I take this off or leave it?
Oh, excuse me. I have a question for the first part. You said in the lattice that it grows in layers around the circle, or around the square or something. Yeah. But then you said that there's like favorite directions for it to grow or something. So how does it work? You know, because you're like growing in layers so as to become like bigger squares. So,
right.
But then it became like something like, for example, the circle was becoming something like in a different shape, no longer a circle, because it has a direction to grow.
So it depends on the model. So yeah, so I was when I was talking about the two-neighbor model, everything is symmetric, everything is lovely, it just grows like squares. If you take an arbitrary model in d dimensions, then, so we don't actually know how to prove this. So the way that we control the growth is by defining a particular polytope. So we choose a set of directions, some of them stable, some of them not stable, and we show that you can infect this polytope, and then as the polytope grows with the same set of faces, then you can infect it layer by layer. So that's how we prove the upper bounds, is by choosing a polytope and using it to control the growth. To prove the lower bounds, then you have to somehow contain your growth. So there we use much simpler polytopes, but the problem is you have to control the growth on the side of one of these things, but not just that, the growth on the side of one of those things, and the growth inside. So we end up looking at things that look a bit like sort of some higher dimensional version of this. So imagine like a bunch of half spaces, all at very slight angles to each other, and then you have sort of a little bit of infection here, and you want to sort of try to control this, sort of put it in some kind of box. So a lot of the work is dealing with the behavior of these objects. So it turns out actually that one of the most difficult steps is proving some sort of subadditivity lemma for these kind of what we call icebergs in high dimensions. It ends up being very technical.
Was there any chance for these simple models to become something different from a square or something, because it hasn't got like, you know, a favorite position and like a favorite direction, and then it becomes like out of the blue, it just, you know, explodes to like a jagged thing?
Right. So one of the reasons that these things are much simpler to understand than things like the Ising model is we don't have to worry about so much about very atypical behavior. So we're trying to prove things home with high probability. So we're trying to bound the probability of the thing growing, so we can look at the most likely way for it to grow. However, if I understood the question correctly, there are lots and lots of questions of that type that one could ask that seem very interesting and nice questions to ask that have not been explored, I think. So, I mean, we're sort of answering the most obvious basic question here, but there are many other directions in which you could take things, for sure. Yeah.
Thank you. I was just thinking of like chaos, you know, or something that could like run out of hand, you know. So yeah.
Right. So because the thing is monotone, we can choose the order in which things get infected. If you look at something more like the Ising model, where things are happening, you know, in real time, you don't get to choose in what order things happen, then life gets way, way more complicated. And really, Ugo's the right person to talk to about that rather than me. It's sort of super surprising to me, at least, that this can say anything about those situations. Yeah, because they're much more complicated.
Thank you.
Yeah.
Any other question?
Thank you very much for an interesting talk. Sure. So you're describing here discrete situation on a lattice, yes? Yeah. But like what you describe remind me very much the dynamics of reaction diffusion equations. They also have some preferable directions to grow and something like this. So do you know any connection to reaction diffusion equation? Distance, yes, or the lattice tends to 0, maybe it can be approximated or something of this kind.
So I'm afraid I don't know anything about that at all. But it sounds very interesting, so I'll be happy to talk about it. But yeah, so I know nothing, sorry.
Okay.
Yeah.
Well, there are interacting particle systems which describe reaction diffusion equations.
So inspired by the previous question, have you seen a continuous version of this model where U is a collection of open sets and then just...
Right, so I did at some point think about a version, sort of a two-neighbor version of this, where you might infect squares randomly, say, in R squared, and then if two squares are close to each other, then they form a larger square. Which I think you could, that kind of thing you could probably do with similar techniques. I didn't actually try to push it through. I mean, I guess that would be an example of what you're saying, if I understand correctly. Yeah, so these things seem very nice. I mean, especially if you can find some sort of some different kind of behavior, then yeah. I mean, if it were just a matter of the techniques work, then it's not so exciting, I guess. But if it's really the techniques break down and there's some different behavior, then I think it would be very nice, especially with some nice application. Yeah, I can't remember what my motivation was. There was some application in mind when I thought about it. I forgot what it was. It was a long time ago. Yeah.
Can you replace the integers or the tori, as you say, by something different, so with other topology or other groups? Or?
Right. So the global topology, I think, shouldn't matter so much. It doesn't really matter on the torus rather than on a square or something. Really what's happening is on a very tiny, tiny scale. If you change the lattice to a different lattice, that should, because the U is so general, I think you should be able to encode any model on any lattice. You should be able to transform it to ZD, I think. Yeah, so I don't have a proof of that written down or anything, but yeah. So one question that I've been asked is whether you can do the same thing on, say, the Heisenberg group, and that really does not fit into this. So if you have your axes doing different things, you sort of lose the homogeneity. And then there are some apparently very interesting questions. Gabor Petter and Joji Balog and Yuval Perez wrote a paper about this. And so Gabor Petter asked me the question, and I think it's related to something in group theory that I also don't know about. But yeah, there do seem to be very interesting questions on sort of different kinds of, I'm not sure if that was the kind of object you were thinking of. Yeah, so. So on different groups, Cayley graphs of different groups, it seems to be an interesting question.
Yeah, that's motivated by things I did as a physicist about 50 years ago. But did you play with hexagonal lattices?
Uh-huh.
Because hexagonal lattices, for a square lattice, if you have a positive correlation, time you come back, it's always after an even number of steps, and it will be positive. Well, if you have positive and negative correlations, if you look if you have a hexagonal lattice, you both have positive and negative interaction. So qualitatively, sometimes it's different. For instance, same problem with cellular automata for simulation of turbulence. They realized that for that to work, they needed to take hexagonal lattice rather than square lattice. So did you play anything anyway?
So I'm not certain that I answered the question correctly. It sounds, if you're talking about negative correlation, it sounds like you're talking about non-monotone models. Because
yeah, other models. I mean, I didn't have time to think about this model in particular, but I know that you looked at different types of problems of this class. So have you played with the difference between hexagonal and square lattice? That's the question.
So I don't think the choice of the lattice matters. So because the family is completely arbitrary, then I think if you took a model on the hexagonal lattice, you could define a corresponding model. I think our result would just prove it for any family on the hexagonal lattice. Yeah, I think you can just basically apply the result and it would be the same. Yeah, so I think that so perhaps I should have said this, that by choosing this U to be completely arbitrary, then the lattice kind of disappears. So I mean, when you're proving it, you don't think about the lattice at all. It's just, okay, there exists some lattice points, but you don't ever have to use the properties of ZD. We don't use any properties of ZD in any of the proofs at all. Yeah, it's just homogeneity, just that is a lattice. Yeah. Yeah.
Any other question? Well, if not, let's thank Rob again.